So when we're looking at this equation right here, it's going to be the same as when we were doing equations before. Does that make sense?
Right.
When we see these guys interacting, obviously there's going to be partners that switch. So these guys would switch places. Does that make sense?
Right. Is it if both are aqueous, is it always a double displacement where they switch partners? So is that
great? Yeah, is
that what it is?
Because actually the way that we want to write this, because they're both aqueous, that means that they're not actually together. Does that make sense?
I think so. Yeah.
So it's like the salt example,
okay,
where we had NaCl. So we can have sodium chloride in its cube form, in its solid state, but then as soon as we add it to some water, it all of a sudden gets dissipated and we no longer have that solid, but we have sodium and chloride in the water. Does that make sense?
That makes sense.
So this is sodium chloride solid, and then NaCl aqueous is this right here.
Okay.
And so all these two pieces are in the solution, but they're not necessarily associated with each other.
So can you pretty much bet that if there's if it's aqueous, if there's something that's aqueous, one of the products is going to be water?
So water is not necessarily a product in this because it's more of it's the solvent. And so it's just facilitating the reaction. Does that make sense?
Yeah.
It's like the medium that the reaction takes place in. And so without the water, we couldn't have these guys broken apart and make it so that way they could switch. Does that make sense? Because basically what we're saying, if I draw this out right here, we're saying that we have a glass full of, I'm going to say that potassium is a star and that OH is a square. So we just have these guys floating around in the solution, and we have another cup that's filled with magnesium and chlorine, and I'm going to say that this guy's a triangle and this guy's a circle. And so what we're doing is we're just basically adding together these two cups. And so what we're going to make is this. Not necessarily in that order, but this is just kind of illustrating what's taking place in the reaction. So is this making sense so far?
Right. It does make sense.
Cool. And so once we have this, so it's basically these guys are coming together, forming this, and if we look at our solubility chart, that's going to tell us what's going to stay aqueous and what's going to be insoluble when they're combined. Does that make sense? And so, for example, if we have a potassium and he bumps it into a square, are they going to rejoin again, or are they just going to stay separate? Or if the potassium bumps into a circle, which is chlorine, are they going to stick together? Does that make sense? And so we look at our chart, we know that on our chart, potassium is one that is always soluble. If we look at our chart, let's make sure that we're looking at this right. So potassium compounds, there's no insoluble exceptions. So potassium, when it's put in an aqueous solution, will always remain soluble. So this guy, we know he's not going to be in the net ionic equation because he's just going to stay floating around in the water. So it's almost like he's not there.
Okay.
Does that make sense?
Makes sense.
And so we can just kind of erase him from this illustration that we've drawn. And so now we keep looking. So let's look at OH. All of these will have charges too. So OH, what's the solubility chart tell us about OH?
It's has an asterisk. It says strong bases.
Right. So
Dioxide.
OH is only soluble if it's part of a strong base. So you'd want to memorize your strong bases. So that's basically anything on the first two columns of the periodic table with OH is going to be a strong base. So this.
So anything with OH.
Yeah, any of these guys on the periodic table, right? Okay, so we know that if the OH, because KOH is a strong base, that's on our strong base list, right?
Mhm.
So this is a strong base. So we know that if these guys bump in together, they're not going to form a solid. They're going to stay separate. And then we can let's look at these guys. What does it say for chlorine?
Chlorine is, it's generally soluble, but with the exception of with silver or lead.
Okay, and we don't have silver or lead in this problem, right? So we can just say that this is always, for this case right here, it's soluble. So we can erase the circles out of our diagram. So basically, what we're saying is that the magnesium and the OH are gonna hook up together, because that's the only things that are left, right? Because there's no rules on our chart that we have for magnesium,
Okay.
right?
Right.
And so his solubility is just basically based on whatever everybody else is in the solution. And so what we're going to end up saying here, because if we write out this the long way, we would say 2K aqueous, and that's going to be plus, and then 2 plus 2OH, that's minus aqueous, right?
Mm-hmm.
Plus Mg plus 2 aqueous plus 2Cl aqueous.
He was going over in class when he would write it out fully like that. We would pick, or not pick, for each one we would figure out like what was a strong electrolyte and what was a strong or a weak electrolyte. And based on that, if it's a strong electrolyte on both sides, those get canceled. Is that?
That's exactly what we've been talking about.
Okay.
Yeah, so it's just using that word electrolyte.
Okay.
So electrolyte is something that is going to dissolve in water and produce ions.
Right.
And so we know that strong bases are a great electrolyte because they dissociate or they dissolve completely when they're put in water. So we know that this is going to be a good electrolyte. And we know that chlorine is a good electrolyte. We don't have anything for magnesium, but because chlorine is, magnesium automatically becomes soluble because the chlorine's not going to want to be attached to it.
Right.
Does that make sense?
That makes sense.
So for this example, everything is a good electrolyte. So everything was going to be floating around. But that's something good that you brought up.
Okay.
So perfect. And then, of course, like we said, we're going to cross out anything that's not doing the chemistry. So we've already eliminated potassium. We've eliminated chlorine. So then basically all we're doing now is just adding these guys together, right? And so we would just do MgOH2 solid. And that would be our answer. And so the net ionic equation would be this right here. Just this and this end part right here.
Mm-hmm. Okay.
Does that make sense?
That does make sense. Going back, why is it with like chlorine and bromine and iodize? I think that's just so straight. Why is it with silver and lead does it not work out?
I couldn't tell you the exact answer.
Mm-hmm.
It just must be some type of chemistry that, like, the interaction must be strong enough between those two elements that it's more favorable.
Okay.
Because that's basically what it comes down to. Is it more favorable for the chlorine to just be chilling by itself with waters around it? Or is it more favorable for the chlorine to be attached to a silver? And so whatever is more favorable or more stronger of an interaction, that's what's going to dominate.
Okay.
Does that make sense?
That makes sense.
And so the reason these guys become a solid is because their interaction is going to be stronger than the water's interaction with those guys.
Okay.
Does that make sense?
That makes sense.
Okay. Cool. So it basically just comes down to whichever is going to be the strongest competitor is going to win out. And so that's what gives us the result. Did this draw?
Yeah, it pieces it together, yeah.
Okay.
It's nice.
Cool. So let's just keep practicing with this.
Okay. So just based on the memorization, that's how you can tell if something's like going to be a solid or an aqueous.
Exactly.
Because sometimes they're just out there.
Right.
Right.
So just memorize. It's just one of those things. Like,
one of those. Okay.
Yeah, you just got to memorize it. So maybe there's a cool video on YouTube or something to memorize it. I don't know.
I don't know.
But what helps me is just writing it over and over again.
I've done that. He told us a story of how some person like wrote on his hand all these notes, and I guess they caught him in the test. This is like years ago, and I guess they caught him and they had to photocopy his hand and they sent it to him. To like say, hey, this is what the student did. The student dropped out, of course, but I guess he used to hang it on his wall. It's like
it's kind of funny thing that this kid did.
Yeah.